Okay, so this is a pretty core issue to the use of p-values for real data sets because this issue very frequently comes up. There's several ways of getting at this issue, but I'll just start with kind of the simple classic way of thinking about this just in terms of like plugging in numbers. So let's say, for the purpose of argument, that we had 10 p-values that were totally not significant. You know, big p-values like 0.5. I mean, if you just randomly draw values out of the p-value interval from 0 to 1, on average you would get 0.5, right? So I think you'll agree 0.5 is a meaningless p-value. It's not something that rejects the null hypothesis in any sense or form. But if we multiply 0.5 times itself 10 times, we get 2 to the minus 10th power, approximately 1 in 1,000 probability, this would be called if we were interpreting that as a p-value, which would suddenly become looking like it's quite significant. So that right away should worry you deeply. In other words, you know, here we took 10 p-values that were meaningless, and suddenly when we multiply them together, it starts to look like we're getting a highly significant result. What that's basically telling you is that you cannot multiply p-values. This idea that the original data were independent, implying that, you know, you can multiply the probabilities of independent events, that idea does not carry over to p-values. Okay, the reason relates very much back to what I showed you immediately prior to this, namely this whole idea of the p-value of the p-value. In other words, sort of this uniform distribution. So let's be super explicit about what the distribution of our p-values looks like on this 10-dimensional box. Okay? So we said we know for any p-value, by definition, its probability density is just this flat uniform probability. So if we have 10 independent variables, we take their p-values, now we've got 10 independent p-values. There are also 10 independent random variables. So what is the probability for that joint distribution of those 10 random variables representing our p-values? What is it going to look like? Well, its probability density of the joint probabilities, because the random variables are independent, is just going to be the product of those 10 uniform probability densities, which means it's a 10-dimensional box with absolutely uniform probability density equal to 1 over the hypercube from 0 to 1. Okay? There's just this flat probability density in a 10-dimensional hypercube. So, now if we ask ourselves, we got an observation that we can define a new random variable, let's say, for the purpose of argument, maybe I'll do this on the board if that helps. So I'll just record this. So let's say, you know, we've got this hypercube, okay? Maybe to begin with, I'll just show the two-dimensional case. Keep it simple. So, you know, it's going from 0 to 1 on each dimension, right? And let's define that we have some random variable that I'm just going to call pi, which is the product of of our individual p-values that I'm going to call alpha sub I, and that's I going from 1 to n, okay, over the set of our 10 p-values that we're plugging into this, okay? So we've got this random variable called pi, and since the alpha sub I are observable, therefore pi is also observable. So now we can ask the question, as a p-value, what is really the p-value for pi? So what is the probability that we will see pi less than or equal to our observed value pi given our null hypothesis? Well, we know what that is because we know what the probability distribution for pi is. It's just absolutely uniform probability of any value of pi is just equal to 1 on this hypercube, basically the 10-dimensional hypercube. So taking this two-dimensional case to begin with, we have some particular value of, let's say our observed value, let's say that observed value was pi, and so I think you'll agree that the box here that's beneath the line alpha, let's call this alpha 2, this is alpha 1, we have uniform density in this whole little slice here, right? So the total probability is just the integral of this area. If we were to say, what's the probability of falling inside that area? So the total area is just a side length of 1 times a height of pi. So this would represent sort of the kind of criterion for example, for getting this kind of p-value. So the question is, over the set of possible, what is the actual set of values of alpha 1, alpha 2 for which we could get this this criterion to be true? Well, I think you'll see that actually there's a whole range of possible pairs of alpha 1, alpha 2 that even go beyond just this box, right? That would satisfy this product being less than or equal to what we observed. So for example, equally well, if we were up at this point here, we're also going to get the product less than or equal to pi, right? And actually there's sort of a hyperbola. Anything underneath that hyperbola is going to pass, right? So basically what you can see right away is that the total area that's going to be under this hyperbola is actually much bigger than pi, right? Okay? So right away we know that this actual p-value is going to be definitely greater than the actual product. Okay, so we cannot, this is sort of an existence proof that we cannot just use the product as its own p-value. It's not, this is the true p-value that we're actually looking for, right? And it is definitely not equal to just the product, okay? So, long story short, never just multiply p-values as a way of trying to get a significance score for multiple independent observations, okay?